Good afternoon to everyone, and thanks for participating of this seminar in YouTube or in Google Meet. And today we have the pleasure of having the speaker, Professor André Izidoro, from currently from Rice University and also Universidades.
Tá bom, eu fechei lá a transmissão. Tá bom, obrigado por tudo, Márcio.
Estadual Paulista. André, thank you a lot for accepting this invitation. Let me talk a little bit about André. He got his PhD in physics at UNESP in 2013, UNESP Universidade Estadual Paulista. And during his PhD, he spent 1 year, André, in the University of Hawaii. Is it correct?
Yes.
Yes. And then he worked as a postdoc researcher in France, in Université Côte d'Azur and Université de Bordeaux, right? If the pronounce is understandable. And from 2018, he started a job as a professor at the engineering school in UNESP at Guaratinguetá campus. And currently he's at Rice University in Texas, US. And he works mainly in the fields of orbital dynamics and planetary formation. And today he's going to present a seminar, the seminar Planet Formation at Home and Abroad. And the questions will be directed to André after his talk. If you have, if you are following the seminar in YouTube, you can indicate you have a question in the chat. Then I will bring it to André. And if you are in Google Meet, just push the button, raise a hand. And I would like to ask before the seminar starts, please everyone to turn off cameras and microphones. And then, Professor André, you can start whenever you're ready.
Okay, Reinaldo, thank you so much for the invitation, you and Maria, and also Richard for all the technical support yesterday and today. It's a pleasure to have this opportunity to talk a little bit about my research at USP. And let me share my screen. So let's So I hope everyone can see the first slide of the talk right now.
Yes.
Yes, please click on the
perfect.
hide button on the hide.
Okay.
Please.
Okay. Oops. What happened? Okay. So I'm going to talk a little bit about planet formation at home and abroad. And after I came out of this title, I realized that this is a very appropriate title for this moment, because most of the planet formation stuff that I have been doing the last year has been made at home. And because of course of the circumstances that we are living right now. But I'm going to talk a little bit about planet formation in the solar system and also in other planetary systems that we know. So this is a seminal plot that shows as the sample of planets that we have discovered so far. So the horizontal axis shows the orbital period of these planets, and the y-axis show the masses if you use some approximations to estimate the mass. We don't have the masses of all planets, but we can just extrapolate to have a sense of the mass of these planets in some of these systems. So the color shows planets that have been discovered by different detection techniques, and it's very appealing. It's very easy to group these planets that have been discovered so far in different groups. So you can also add the solar system terrestrial planets in this plot. Unfortunately, we don't have a lot of information of planets that are as small as the Earth, or even the planets that are as far as the giant planets in the solar system yet. But you can study essentially what's it's driving the formation of these planets that they are very close to the stars. And we do know right now that you have many planets like this around other stars. So typically, we divide these planet systems or these planet classes in 3 groups, or even a few groups. Like we have this so-called hot super Earths. We have a group that's called hot Jupiters, and you have also the so-called cold Jupiters. So hot super Earths, they are planets that have sizes or masses between 1 and maybe 20 Earth masses and sizes of 1 to 4, 3 Earth's radii. Hot Jupiters are Jupiter mass planets that are very, very close to the star and have very short orbital periods. And cold Jupiters are planets that are a few AU from their host stars. So in this talk, I'm going to focus essentially on trying to model the formation of hot super Earths, and also to put how the solar system fits in context of these systems that we observe around other stars. So just to make a very important point of this talk. So these hot super Earths of these hot Jupiters, they are orbiting their stars at orbital periods much shorter than the orbital period of Mercury in the solar system. Mercury has an orbital period of 80 days. And most of the super Earths, the hot super Earths that we observe around other stars, they have orbital periods shorter than 100 days. So the question that I want to address today is, what does set the destiny of planetary systems from producing something like this, or I mean, the terrestrial planets that we have in the solar system, from something like this, that maybe that how super Earths look like, or even gas giant planets. So let's first define very clearly what we mean by super Earths. Not exactly this, but super Earths are planets, as I said before, that have sizes between those of Earth and the ice giants in the solar system. So sizes essentially between 1 and 4 Earth's radii, and masses between 1 and 30 Earth masses. So what do we know about these super Earth systems? So we know they are very common. And you have some iconic systems of multiple super Earths. The first one is probably one of the most famous systems, is TRAPPIST-1 system that has 1, 2, 3, 4, 5, 8 super Earths, 7, I think it's 8 actually. With orbits with very short orbital periods. If you put the solar system here for reference in terms of the TRAPPIST-1 systems, this will be the position that these planets are orbiting this low mass star. But we have also some very iconic systems around solar type stars, like the Kepler-11 system. The Kepler-11 systems have 5 planets inside Mercury's orbit. And from statistics, we know right now that the super Earths, they are observed in about 30, maybe 50%, maybe even more of the solar type stars. So super Earths, so planets with sizes between 1 and 4 Earth's radii, they are very common around solar type stars. So these planets, they typically come in multi-planet systems. So that means that they have more than one planet around the same star. So these planets overall, they have very compact orbits, but they are not resonant orbits. I will talk more about that later in the talk. And also, observations suggest today that these innermost hot super Earths, they are probably rocky. So they look like the Earth, maybe, but they don't look exactly as the ice giants in the solar system. They're not water, ice-dominated planets, but most likely rocky planets. At least the innermost ones and those that have lower masses. So how does super Earths form? To address these questions, let's take a look at the current view of planet formation that we have. So we know that planet formation starts in a disk of gas. So we have a young disk rotating around a young star. So this disk is essentially composed of gas and a little bit of dust. And this dust essentially collides and coagulates in larger grains. So these larger grains we call pebbles. And pebbles will be a very important part of the story that I'm going to tell you today. So pebbles are like rocks that you find on the streets, like rocks that you can carry in your hands. So that you can imagine as a pebble being. So in this protoplanetary disk, because of the gas, these pebbles, they feel a gas drag. So, and these pebbles, they start to spiral inwards in the gas. So I'm going to explain why this happens very quickly. So if you have the star and one single pebble orbiting the star, so you have these pebbles feeling essentially the central force from the star. So the star is going to force the pebble to orbit at velocity given by the Keplerian velocity. But the gas feels also the gas pressure, not only the central force from the star. And because of that, the gas speed around the star is slightly lower than the Keplerian velocity, just less than 1% lower. But this is enough to make these pebbles that are orbiting the star at Keplerian velocity to feel a headwind. And this headwind makes these pebbles lose energy and spiral inwards. That's what we call gas drag. So that's the same thing that you feel when you ride your bike on the street. So pebbles, they feel a headwind and they lose energy and spiral inwards. So these pebbles, they might concentrate into clumps. So clumps means that there are regions in the disk that are overdense. If there's enough pebbles, there are a lot of pebbles that concentrate in one specific regions of the disk, these pebbles might collapse because of the self-gravity of the clump. And that's when planetesimal formation happens. Planetesimal formation happens there's a jump from particles that have millimeter and centimeter size particles to particles that have sizes of hundreds of kilometers. So that's how pebble accretion is. Pebbles are converted in planetesimals. Planetesimals are the building blocks of the planets, and they have size. You can associate them today as today's asteroids that we see in the solar system. So how planetesimal formation proceeds once you have planetesimals in the disk? Planetesimal formation can proceed in two different ways. So we can accrete. Planetesimals can grow further to what we call planetary embryos. Planetary embryos, you can imagine something like the size of the moon. So planetesimals can go via collisions with other planetesimals, or it can go via pebble accretion. So if you have a planetesimals that forms in the disk, and you have a flow of pebbles that are spiraling inwards because of gas drag, so when these pebbles pass by the planetesimal gravitational field can pull the pebble from the gas and accrete it. And you can grow to planetary embryos from via these two different processes. Just one simulation to show how this works. Here is a simulation showing there's one planetesimal in the center of the simulation here. So you're gonna release two different objects at the same position in the disk. So this green region here shows the gas in the disk. So if you release the planetesimal and the pebbles, that's what happens. Both feel gas drag, but the drag that the planetesimals feels is much weaker than the drag that the pebble feels. So the pebble is more efficiently accreted than one planetesimals. And why I'm discussing this? Because this is very important to explain how giant planets form. So if you estimate, we know that giant planets, they probably, at least a fraction of them, they grow from cores that have sizes or masses of at least 10 Earth masses. So to grow a core like the ice giants in the solar system, like Uranus and Neptune, via planetesimal accretion, would take too long. So this is what this plot shows. So this the horizontal axis shows the distance from the star, and the y-axis shows the accretion time scale. So let's take a look at the solid line first. So the solid line shows how long it takes to grow one object of 10 Earth masses at, for example, 2 AU. So you can see that via pebble accretion, the time scale is about 10,000 years. So even if you want to grow, let's say, the ice giants at 30 AU or so, Uranus and Neptune that have masses of about 20 Earth masses each. So you do only take about 100,000 years to grow one planet of 10 Earth masses. But if you look at how planetesimal accretion works, it's much more complicated. If you look at now at the gray line, gray solid line, we can see that the accretion time scale of a body of 10 Earth masses at, let's say, 5 AU, it's longer than the typical gas's lifetime. That is between 1 and 10 billion years. So if you want to grow Jupiter fast enough, and then make Jupiter accrete this gas envelope that it has today, you have to do it quickly, otherwise the gas is gone in the disk. So it's very hard to grow a giant planet core via planetesimal accretion at largest distance from the star. So that's why pebble accretion became so popular in the last few years, because it solves essentially this problem, this accretion timescale problem of giant planet formation. As the planet is growing in the disk of gas, this planet starts to interact with the gas around its orbit. So here it's a simulation showing this process. Here's the disk. Okay, so here's the planet. So this is just a box that we took a frame from the disk. So you see this region that's low, that's darker. That means that the density of gas in this region is slightly lower compared to these lighter regions. And you see these waves that arises from the gravitational interaction between the core, like, see, this is a 20 Earth mass planet. This planet is interacting with the gas and launching these waves. And this interaction changes the disk structure. So remember that I said in the beginning of the talk that the gas orbits the star at sub-Keplerian velocities, slightly lower the Keplerian velocity. So when the planets interact with the gas, might speed up the gas, and the velocities of the gas may become super Keplerian. Why this is important? Because if you have pebbles drifting from that region of the disk, let's say beyond 1.4, the position of the planet here. So the pebbles is drifting inwards because it's feeling a headwind. But then when the pebbles arrives at this location, the velocity starts to be super Keplerian. So the gas drag vanishes. And in fact, these pebbles, they start to drift outwards. So that means that if you have a planet growing by pebble accretion in the disk, so the planet is growing because there's a very efficient or very high flux of pebbles spiraling inwards and feeding the growth of a planet in some location of the disk. But eventually, when the planet becomes massive enough, that I mean about 20 Earth mass or so, the planets change the disk structure and stop accreting pebbles. That's what we call pebble isolation mass. So the planet that is larger than 20 Earth masses, it cannot grow via pebble accretion, via this, because it changed the disk structure. Stop growing. So this is, of course, this very mass depends on this disk properties and some other things. But so just to continue, so these planetesimals, they grow via to planetary embryos, maybe via Pebble accretion, maybe via planetesimal accretion. And also the gas is still around. If you grow to masses large enough, so like the masses of a giant planet core, larger than 10, 20 Earth masses, these planets start to interact with the disk, and also migrate. So when the planets interact with the disk gravitationally, the planet launches these spiral waves. And this makes also the planet to migrate to the disk. So if the planet is not massive enough to open a wide gap, so we call this migration regime of type 1 migration. If this blue planet right here, eventually, let's say a giant planet core becomes Jupiter or a gas giant, then so the planet is massive enough to open a large gap in the disk, and they migrate in the type 2 migration regime. So planets that are massive enough, they move during the gas disk phase because they interact with the gas. So we have two ways to move in the disk. So we move when the pebbles are very small because they feel gas drag. And also if you become massive enough, then the gravitational interaction between the planet and the gas becomes important, and you also might move because of this interaction. So you have two different processes at play here, for very small, very low mass objects and for massive objects. After the gas is gone in the disk, that typically takes between 1 and 10 million years, you may have a phase of giant impacts and maybe build the terrestrial planets or the ice giants in the solar system. So that's a very summary of planet formation, how we think planet formation happens around other systems and also in the solar system. So I'm going to explain a little bit more about type 1 migration because it will be very important for this talk. So as I said, planets that have masses larger than 1 and up to 20, 30 Earth masses, they interact with the gas and they migrate. So if they are not massive enough to open a gap, it's type 1 migration regime. That's the regime that you're going to focus on in this talk. So here you have just a simulation. This light dot here shows a star. So this orange region shows a disk of gas around the star. So you're going to put a planet in the disk and let it evolve with the disk. And so it starts to excite these waves and to migrate. So this migration, it can be inwards and can be outwards, depending on the thermodynamics of the disk and the planetary masses. So it's a little bit complicated. But there are some migration maps that gives the direction and speed of migration of planets with different masses. So what we're going to do is to use this to conduct some any-body simulations later. So here you have a migration map for one specific disk model. So you have the distance from the star and the horizontal axis, the mass of the planets, and the color shows the torque that the planet feels when it interacts with the gas. So a yellowish color means that the planet is moving outwards because of the torque, because of the interaction with the gas. And a darkish means that the planet's moving inwards. And this is for a younger disk, and these structures, they change in time. So the gray line shows the region where the torque is 0, the torque vanishes. So the planet is not moved. So but these regions, because the disk is dissipating in time, is evolving in time, so these regions move. So just to make sure that I'm clear about that. So if you have a planet of about 20 Earth masses, and it grows at near 0.1 AU in this disk, it's going to migrate outwards. The planet is lower mass, like 5 Earth mass, and grows at 2 AU or near 2 AU. In this early stage of the disk, is going to migrate inwards. And the same here, if your planet is inside this region, it's going to migrate outwards because of the torques that comes from the disk. So the disk is evolving and dissipating, and so these regions change in time. So eventually, most planets And during the late stage of the disk, virtually planets larger than 10 Earth masses are free to migrate inwards in the disk. Of course, if there is enough gas to bring them inwards. So what we did was to include all these ingredients of planet formation in any body code. So the code is called Flintstone and includes several effects. So you have a gas disk model that based on the work of Bertrand Beach. This model includes viscous heating in the gas, stellar radiation, and the effects of radial diffusion. We also assume that the disk has a planet track at 0.1 U. So the disk is not fully connected to the star. So the planets that are migrating inwards, they do not fall into the star because the star is just connected to the planet. There's a trap, so a transition in the surface density of the gas that avoids planet to fall into the star. You have also gas accretion onto the cores to simulate planetary gas giant planet formation. And you have the effects of type 1 and type 2 migration, and also Pebble operation. So we include some prescriptions of type 1 of migration and Pebble operation into any body code to perform some simulations to see what comes out when we try to build systems as we observe. So just to explain how we do that, how we model this, the initial conditions of the simulations, we have the disk. The disk is initially hot inside, we call hot inside the snowline, or the temperature of the disk is higher than 107 kelvins. So snowline, I mean the region of the disk where water would condensate as ice beyond it. And you have this cold region. So we believe that pebbles in the cold regions of the disk, or I mean beyond the snowline, they are probably larger than pebbles inside the snowline. So these millimeter-sized particles that I mentioned in the beginning of the talk, so they drift inwards. But pebbles in the other parts of the disk, they are probably larger because the ice is probably more sticky, so they can grow more efficiently to larger sizes. So, but remember that these pebbles, they're going to drift inwards because of a gas drag in the disk. So this snapshot here shows the very, very early stages of planet formation. So there's only the gas and the first dust that has coagulated to pebbles. And this dust starts drifting inward as they grow to the size of pebbles. As they grow, so if the dust reaches regions of the disk that's too hot, for example, like regions where the disk temperature is higher than 1,400 kelvins, so they probably evaporate, and you might recycle or accrete some of them into the star. And pebbles, icy pebbles that drift inwards, as they cross the snowline, we assume that they fragment in smaller grains, and we also assume that they lose the ice component because they are in hotter regions of the disk. So icy pebbles crossing this low line in the model, they sublimate, released only the silicate small grains in the inner parts of the disk. And these pebbles, they eventually form planetesimals and planetary embryos. And the simulation that I'm going to show here start assuming that we have a distribution of planetary embryos inside the snowline or outside the snowline. So typically with moon, of the sizes of these bodies or the masses are initially about moon mass. So one of the questions that we want to address is what does decide the destiny of planetary system, right? So one thing that we explore in the simulations is how much mass we have to make the planets, to build the planets. And this is essentially translates to what we call a pebble flux. So a pebble flux that I'm going to refer here shows how much mass in pebbles is available in the disk to build planets. Okay. So let me go to the next slide. So I'm going to present us the result of one simulation, what that has what we call a low pebble flux. By low, I mean the total mass in pebbles drifting into the disk during this few million years corresponds to about 190 Earth masses of pebbles. And here is the result. So let me explain this plot. So each line here shows one planetary embryo in the simulation. So here, let me explain first the axis. So the horizontal axis shows time. So the top panel shows semi-major axis, and the y-axis and mass, and the y-axis in the bottom panel. So each line here shows one planetary embryo that we assume to exist in the disk. Their initial masses are about like moon mass. And so as you can see here, they have very low mass from the beginning. But then there's a flux of pebbles drifting in the disk. They start to accrete these pebbles and grow, as we can see here by these curves. So we can see, for example, here in these regions of the plot that these objects are growing via pebble accretion. As they grow, so because in the beginning they are very small, so they're small to type 1 migration make them move, and they are too large to gas drag make them move. So they basically stay where they are. So, but as they grow to larger masses, to masses of about a few Earth masses, as you can see here at this point, so they start to interact with the gas and start to move inwards. So as you can see, the color line shows the final objects that survive at the end of the simulation. And this black one shows the objects that were accreted or were ejected from the systems, or the objects that are too far beyond 100, that have orbital period larger than 100 days. So you want to look at systems that produce like super Earths or hot super Earths. So you don't care too much about the systems that have planets beyond 1 AU at this point. So, okay, so if you have a pebble flux of 190 Earth masses, so you have some embryos growing the disk, and you just allow them to accrete a flux of pebble of about 190 Earth masses. Of course, not all this mass is consumed by the embryos. Only a tiny fraction of it, like a few percent. They grow to masses that have about the right size for super Earths, something between 1, 2, and 7 Earth masses. If you have a higher pebble flux, the result is different. So I forgot to say one thing important about this first plot. So in the first plot, you see these jumps in the mass right here. So and I mark here that they are collisions. So when these bodies are migrating inwards, they eventually might collide with each other because of the gravitational interaction in the system. And they grow even further, as you can see, for example, in this jumps in mass right here. So these most show collisions in the system. If you increase the pebble flux, means that you have more material to build the planets. So the evolution is very similar, but the final masses are dramatically different. So here, the final mass of the planets at the end of the gas disk phase, 5 million years. It's lower than 10 Earth masses. And here, in the simulations with a higher pebble flux, is 50 Earth masses, the most massive object. So this kind of disk with this amount of pebbles available to form planets don't make systems like super Earth. They probably make systems like giant planets or gas giant planets. Okay. So, and this simple increase in the factor of 2 in the pebble flux from 190 to 380 is enough to bifurcate the evolution of the system. So from making something like super Earth systems to something that might be like the cores of giant planets. In this particular case, we don't have gas accretion in the simulation for these objects. These objects, they will not become gas giants because they are too low mass. But these ones, if you turn on gas accretion, if you allow them to accrete gas in the disk, they'll become planets larger than, or even as big as Jupiter. But the question is, are these super Earths that we produce in simulations with a low pebble flux, or sufficiently low pebble flux, rocky or water rich? So we know that photoevaporation models suggest that the innermost super-Earths are mostly rocky. But then there is also some interpretation that suggests that super-Earths larger than 2 Earths radii may be water worlds. We have a lot of water. So we have this debate currently, but it's very possible that at least the innermost super-Earths of the systems, they are rocky. I mean, they are not like the ice giants in the solar system, probably. They are much more drier, or maybe even drier than the Earth. Okay, so we know how to produce this super-Earths. So here's the simulations that make it easy to understand what we are simulating. So this gray region here shows those curves that are shown in the migration map. So if the planet is inside this region, it's migrating outwards. That's the take. And here you have this snow line in the disk. So this is distance from the star, this is mass. And each dot here shows one planetary embryo that's going to grow via pebble accretion and via collisions as well. So there's a flux of pebbles that's it's not high, but it's not super low. It's just the right one to make some systems of super-Earths. So the pebbles are going to drift and pass these objects, and they are going to grow via pebble accretion, as I showed in the previous slides. But here's a difference. It's a movie showing this growth. So they grow via pebble accretion. You can see that they grow mostly beyond the water snow line, and they have like the composition of this body is dominated by water. They accrete a lot of water. Because they form mostly beyond this snow line. You can see that you have, at the end of the simulations, 5 million years at this point, several planets that have sizes or masses between 1 and 5, 10 Earth masses. That looks like some system of super-Earths that we observe. But the point is, in this case, so all the planets that have very water-rich composition. This might not be what we observe in the super-Earth systems. So what do we need to produce then some rocky super-Earths? So in the previous simulation, I assume that planetesimal formation happened beyond and inside the snow line. Here we assume that planetesimal formation starts actually inside the snow line to see what happens. Because we know planetesimal formation is not strongly constrained. As the disk evolves, these simulations, they grow in the inner disk. And finally, in this case, so you have a system of planets that have masses around 5, 10 Earth masses. And the innermost ones are indeed planets with rocky compositions. So in fact, there is a diversity of super-Earth compositions that could come from this model. So you could produce systems that are essentially only that the outputs are water-rich. So you could produce systems that have a mix of water-rich and water-poor planets, and some systems that are dominated by water-poor compositions, planets. And this depends essentially where planetesimal formation happens first, or where it's more efficiently. If planetesimal formation is more efficiently in the inner disk, I mean, be inside the snow line, so it's not so difficult to produce rocky super-Earths. But if planet formation or planetesimal formation starts first beyond the snow line, and is very efficient beyond the snow line, it might be very difficult to avoid producing some systems with water-rich compositions. So we have to constrain now how planetesimal formation really happens to understand which scenario is correct. But we can still use the systems to look at the dynamical structure of planetary systems. So we have from observations the orbital periods of these planets. So that's because most of these planets, they are observed by transit, and that's one of the best metrics that we have, that we can use. So if the planet is transiting at least twice around the star during the time that we're observing it, we can estimate, we can get the orbital period of the planet. So if you have multiple planets, like in this bottom figure here, that are orbiting the star, so each one of them should have different orbital period. And you can look at the period ratio between some pairs to study the kind of orbital configuration that these planets evolve. So if the period ratio between, for example, pair 2 and pair 1 is a ratio of integers, it means that these planets, they are near or in a resonant configuration. So what we're going to do right now is to compare essentially the orbital configurations of the planets that we produce in the simulations of the planets that we observe, of the planetary systems that we observe. And this is the data that we have. It's not so updated, this plot, but things did not change too much since then. So here you have the distribution of period ratios of planets that we observe. So we can see that there's the period ratios varies essentially of different pairs, a little bit beyond 1 and 4. And if you have a planet, so if you have many systems that pile up at some specific locations, for example, the 3, 2, 2 here, 3, 2. So that means that these planets, they are in a resonant configuration, as I said before. So that means that the innermost planet is orbiting the star 3 times, and the outermost planets 2 times. So they have a synchronous motion around the star. So that's what we call resonance. So you can have different resonances that like the 3 to 2, 2 to 1, and second order resonances, and so on. So by resonant chain, that I'm going to use a lot this term here in this talk, I mean a system that's very compact, and all planets are in a resonant configuration. What we know from the Kepler data is that most of the planet pairs, they are not resonant chains. They are not in resonant chains. They are more spread and non-resonant, at least in terms of resonances of first order. And here's a plot that shows this. So here's the period ratio of planet pairs. For example, planet P2 and P1, Kepler systems. So here's the gray one, shows the Kepler distribution. So we can see that there's no clear pileup of planets at specific resonances like the 322. Maybe there's some slightly pileup here, but it's not very significant as compared as the result of my simulations at the end of the gas phase. So as I simulate my systems, and I let the disk evolve for 5 million years, I show you that these planets move inwards, and they typically park near the star. But they don't park in any random configuration. They typically park in a resonant configuration. That means that you have some synchronous motion between planets in the systems. So you can see here that most of the planets that I produce in my simulations at 5 million years, they are in some specific resonant configurations. For example, a large fraction of them are in the 4 to 3, or at least near the 4 to 3. So we cannot say for sure that they are resonant. They have resonant configurations, but just by looking at this plot, you have to look at other quantities. I'm not going to talk about this right now, but this gives some indications that they might be in resonance, at least. But the point is, the orbital configuration is very different from the Kepler planets, at least at the end of 5 million years when the gas is gone in my simulations. Just to make sure that everyone is on the same page, so here's a resonant configuration of a system that comes from my simulation, for example. So you have the star. So each circle shows the evolution of one planet. And then we can see that these planets, for example, planet red and green, they have very synchronous motions. And all these planets, in this case, they are actually in the 3-2 mean motion resonance. So a non-resonant configuration means that the planets have no synchronous motion like this. That we call resonant chain and non-resonant chain. Then, if you look at the systems that we produce in the simulations, so here is one system that produces super Earths. So most of these planets, they migrate inwards and they pile up at the disk inner edge, as I discussed before, and they have a stable configuration. And by stable, I mean they are in resonant configuration. After the gas is gone, they continued in this kind of evolution. some of the systems, after the gas dissipates at 5 million years, they become dynamically unstable, and they collide and grow further, as we can see here. So we have a fraction of typically 15% stable systems in the simulations and 85% unstable. Unstable, I mean, they became dynamically stable after the gas dispersion and finally reached different configuration. Here's just one movie showing this kind of evolution in a different view. So, start again. So the planets, here's the star, the gas is the gray region. So the planets migrate inwards. I think the movie is... since the movie is not playing so well. Yeah, but the idea here of this figure was to show that these planets, they would migrate inwards, the orbit would shrink towards the star, and then, no, it's not playing, sorry. So the orbit would shrink towards the star, and then eventually this orbit would become dynamically stable in some cases, and in some cases not. So we do have some evidence for stable systems or for resonant systems, the Kepler data. For example, the Kepler 223 planets that have 4 planets in this resonant chain 4-3, 3-2, 4-3. And you have also older planet systems like Kepler 80 and TRAPPIST-1. So we can finally conduct some transit observations of the systems that we produce, the simulations, to compare with the Kepler sample. Of course, we cannot compare the planetary system that we produce in the simulations with the Kepler sample directly, because the Kepler sample has some observational bias. You have to include this observational bias and the simulations that we have to then finally compare with the Kepler planets. And when we do that, so the simulations that we have, both for water-rich or rocky super-Earths, they match the Kepler sample very well. So that's what we show here, the black dashed line. So if we mix a fraction, typically of 10% of stable systems, of resonant systems, with a fraction of 90% of unstable systems, we match the Kepler period ratio distribution. We cannot match the Kepler sample period ratio distribution at the end of the gas disk phase. But after the systems evolve for tens of millions of years, the systems typically become stable, and you can match the period ratio distribution. Another quantity that we can look at the Kepler planet multiplicity, that we know that most of the Kepler planets that we observe come in single planet systems. So we have several systems that have 2 or more planets, but most of them come in multi-planet systems. And this is what we call Kepler dichotomy. So why so many systems of super-Earths have only one observed planet? And the simulations that we have performed try to explain this. So the reason why we cannot, in fact, the simulations propose that. So the Kepler dichotomy is just an observational artifact. So it's not real, and most of the systems probably have older super-Earths that are missed by transit because they have inclined orbits. And here is the plot that shows what we get when you compare the period ratio, the planet multiplicity distribution of the Kepler sample with the results of our simulations. If we mix a fraction of 5% of stable systems, the green dashed line, with 95% unstable systems, we can see that we match the Kepler dichotomy very well. And that's, as I said before, that's because most of the planets at the end of the simulations, after they become dynamically stable, they gain some inclination, some mutual inclination. So when you observe them by Kepler, so planets that have mutual inclination, they are missed in transit, but you can only observe planets, out planets in the systems, if you look at from the right point of view, and also if the planets have very low mutual orbital inclination. So we propose the Kepler dichotomy is just observational artifact in the data. But how do we place the solar system in the context of exoplanets? So how do we explain the terrestrial planets in the solar system? We know that you have a higher pebble flux, we go to produce the giant planets. If you have the right pebble flux, we produce super Earths. But what about the Earth? How we get the Earth in the first place? So if you reduce the pebble flux, that's what happens. So we have that for a flux of 190 Earth masses, so we typically produce some super Earth systems, as I show here. But if you keep reducing the pebble flux for even lower amounts, so it starts to get even lower mass planets. So here, so in the simulation, so your planets grow, migrate from the other parts of the disk and move inwards, and in the end they have masses between 1 and 10 Earth masses. But if the pebble flux is just 114 Earth masses, so they are slightly smaller. So the total mass in embryos here in the end of the simulation is 9 Earth masses. If you keep reducing the pebble flux, the planets get even smaller. Of course, makes sense, right? If you have less mass to accrete, you have to form smaller planets. Yeah. So we believe that there's something that explains this very well in the solar system. And this might explain why you don't have a super Earth in the solar system. Remember, super Earths are very common, so why don't have one here? So the story is like this. You have this is the disk of the sun, the pebbles start to drift inwards. They do their thing. Then you form the planetesimals, planetary embryos. Beleza. And then what happens is the following. In the solar system, there's one very important observation that has been made that we call the solar system great isotopic dichotomy. If you look at some, if you break some meteorites that we have in our samples and look at them, so you have different classes of meteorites. We have what we call like CC like meteorites and NC like meteorites that you can associate the NC that asteroids or meteorites that came from the inner part of the solar system, and the CC that are meteorites where the parent body was formed, at least in the older part of the solar system. And these different isotopic systems, so for example, titanium, chromium, and other systems, they show that this NC meteorites, they plot in the very different regions of the CC meteorites. So that means that something happened in the solar system to keep these two reservoirs divided or separated. Because if you have pebbles that are coming from the other parts of the solar system and drifting inwards, these pebbles, they're going to mix together. And at the end, if you look at the meteorites that we collect today, they should look out like the same. But that's not what we see. And to explain this dichotomy in these isotopic systems, it was proposed that Jupiter block the flow of pebbles in the solar system. So Jupiter's formation block and avoided that many pebbles from the older parts of the solar system could enter in the inner solar system. Remember the pebble isolation mass. The planet has hit like a mass of about 20 Earth mass. It's changed the disk structure, stop accreting pebbles. But not only stop accreting pebbles, but avoids that pebbles beyond it could enter into the inner system. And how do we get this mix of asteroids or the asteroid belt then today? So that was caused later by Jupiter probably, but I'm not going to discuss this here. So the story is like this. So we have these pebbles drifting inwards. So there's not much mixing during this time, because if there was too much mixing, so the meteorites that you have today, the sample, they should have the same isotopic compositions, but that's not what we see. So we have this formation of the planetesimals, we have the formation of Jupiter. And Jupiter, when Jupiter forms, it blocks the pebble flux from the inner systems. And this keeps the two inner and or other solar system reservoir disconnected. And this explains the solar system is isotopic dichotomy. But this is not the only thing that Jupiter does. When Jupiter grows and block the pebble flux in the inner systems, forced the terrestrial planets to grow via planetesimal accretion and not via pebble accretion. Why not via pebble accretion? Because if it's pebble accretion, it can solve a lot of things. Yeah, but the problem is if Jupiter grows early, and Jupiter has probably to form early to avoid too much contamination between the two reservoirs. What happens is that once Jupiter is formed, all pebbles that are in the inner disk, they drift inwards, or they are lost into the star very quickly. In the inner solar system, pebble reservoir is essentially depleted. So there is no pebble to be accreted. So planet formation in the inner solar system was probably via planetesimal accretion and not pebble accretion. That's a paper that we have submitted and it's under review. We got the first review report. Is very positive and hopefully will be accepted soon. But just to summarize and to close the talk, and that if you have, if you reduce the pebble flux, even at some point you block completely the pebble flux, you might form the terrestrial planets. If you increase the pebble flux, then so you produce some systems of super Earths and then systems of giant planets, because there's more mass and you can grow to larger masses. The system of giant planets, like Jupiter, and here you have super Earths. You can have both systems, both kind of planets in the same systems, and that's what we do observe. But this system of giant planets, they typically become dynamically stable because the mutual gravitational interaction is very strong, and the end of these planets become very eccentric because they evolve during the gas disk phase. Once the gas is gone, they interact with each other and become dynamically stable. And this is very interesting because this kind of evolution is that we see here. So here we have a system of a few giant planets, one simulation by Sean Raymond. It's an old simulation, but can show the point of these two plots very well. So here you have 3 dots. These 3 dots are Jupiter mass planets. They are interacting with some planetesimals that are in the disk, and they eventually become dynamically stable. And we can see that their eccentricities jump to very high values. So at the end, so we have a giant planet at few AU that has an eccentricity of 0.8. And this is consistent with observations because we do know that most of giant planets that we observe have very eccentric orbits. So here's a series of simulations that we published last year that shows that this kind of evolution coming from the simulations of higher pebble flux can match fairly well the eccentricity distribution of giant planets around other stars. So did a similar event happen in the solar system? The answer is yes. And this is what we call probably the solar system giant planet instability or NISI model. So we have this giant planets in a resonant configuration. They eventually become dynamically stable and reach their current orbits. But why the event in the solar system was not so energetic? It's probably because Jupiter and Saturn, they avoid some close encounters during the stability phase. And that's why they did not get more eccentric than they are today. So here's a series of simulations that shows this process. So here you have each dot shows the final eccentricity of Jupiter after one instability simulation, as I showed before. That actually was a cartoon, right? Here is an eccentricity of Jupiter in one simulation where Jupiter has a close encounter with Saturn. Sorry. And finally, here's a simulation where Jupiter does not experience a close encounter with Saturn. So the final orbital configuration of giant planets depends on the violence during the stability phase. And probably in the solar system, it was not super violent. And that's why we have solar system giant planets in low eccentricity orbits. So, but all this puts the solar system in the context of exoplanets. So I think I should let here my conclusions and then take some questions because I'm already beyond the time, probably.
Thank you a lot, André. It is for me that I'm not close to this area of research. I see that things are evolving very quickly, and the research seems to be very sophisticated and also very elegant. The results you showed. So I will open here for the questions. The first, Maria, please.
Yes, thank you very much for your talk, André. I am going to ask a very naive question because I am completely outside of the topic, but it was really, really clear. Thanks a lot for the talk. Well, we learned that the Pebble flux is really important in determining the kind of planet that you're going to form. And I was wondering what is well, we see that a giant planet can block the flux, but in reality, what is controlling this flux? Is intrinsic of each system, or is coming from the medium? It's not clear for me.
Yeah. It could be. Now, you do see, for example, we do know that some high metallicity stars have more giant planets, and so that might be fairly consistent with this idea of having a higher or Pebble flux. But this is also just the problem that if you have something else that could regulate the Pebble flux, like Jupiter or even a pressure bump, then it's hard to say, because what exactly is determining this final masses. I think, because for example, you have ALMA observations shows many pressure bumps in disk. We don't know if these are caused by planets or some disk physics, but or chemistry. But yeah, this could also have a similar role if all systems has very similar Pebble flux. Let's imagine like this.
So you might expect, for example, a high Pebble flux, but then locally something might be producing actually a lower flux.
Yes, that might be the case of the solar system. It's, for example, yeah.
Okay.
At least in terms of explaining the formation of the inner system.
Yes.
So.
Okay, thank you.
Sure.
Please, Jorge.
Hi, André. Very nice talk.
Thank you.
From your simulations, I'm trying to couple it with some Kepler observations and so on. Can we say anything about how common is the solar system?
Yeah, it's complicated. Yeah, the problem. We don't have. We don't. None of the simulations that we have so far can really produce something like the solar system, because, for instance, we don't include in the model some effects that could be very important for the solar system in particular. For instance, we do have this different model for giant planet growth, but then once we have, for example, two giant planets growing in the systems, in our simulations, these two giant planets, they should, because of the model that we use, of the migration precision that we use, these two giant planets migrate inwards. So they don't really interact with each other in terms of their interaction could impact the gas flow in the disk. Because, for example, in the solar system, we know we believe that this Jupiter and Saturn mass ratio, that's about 3. It was probably very important to avoid Jupiter's migration to become something like a hot Jupiter. So because if you have only Jupiter migrating the system, so it migrates all the way from, let's say, if it forms early in particular, that's what we might need to explain the solar system's isotopic dichotomy. We have Jupiter forming at, let's say, 1 million years, and then have maybe 2 or 3 million years to move inwards. And that's plenty of time to reach the inner edge of the disk, or to become a hot Jupiter. But then maybe what happened here is what at least simulation shows, is that we have Saturn, and Saturn, because of the mass ratio, when they form a resonant configuration, they change the disk structure, and migration stops because of the particular mass ratio. So, for example, we don't know how to include this in the code yet. Or we don't have included this in the code yet. So, all the planets that we form essentially, or they migrate all the way from their original location to close to the star, or they stay where they are because the disk viscosity, for example, is too low. So we don't get solar system in the simulations. That's the short answer for your question. So you have to improve something in the model to try to build the solar system. Not sure if this answer completely your question.
If someone else also wants to ask in Portuguese, it's fine. And I have one question. In your simulations, I saw, I think in the beginning of the presentation, slide 13, for example. So when you have to consider the dynamic of gas, the interaction with the planetesimals forming, is relevant any 3D effect, or the dynamics is completely 2D? I mean, because the dynamics of vorticity could be different in 3D and 2D, or the disk is so thin that it's irrelevant.
Yeah, this, for example, in this simulation, we have this pebble isolation mass. Yeah, these are if I remember correct, these are 2D simulations, and yes, the 3D effects could be important, and we, in fact, I said in the talk that we have this pebble isolation mass that blocks all the pebbles, and in fact, this is not completely true. Because so if you have pebbles that are too small or sufficiently small, they can still flow with the gas because they just move along with the gas because they're just too tiny. So you can still have a little bit of leaking of dust by a planet that hit a pebble isolation mass, and 3D effects also could play a role, and even the growth of the planet can also change the dynamics of the dust nearby and make things far more complicated. Yeah, this is something that's not included in the scenarios yet. Yeah.
Thanks.
But these are important facts.
Now, Betty, please.
André, hi. Thanks for the talk. Very interesting.
Sure.
Let me... so according to these pebbles, modeling, migration theory, and the fact that Jupiter might have prevented this migration to the inner regions, therefore preserving the planets and the Earth as it is. So it looks like our solar system is almost like a fortuitous event, right? In the sense that it would be rare then, and therefore we might expect that Earth planets or Earth-like planets would be, if we think about the whole system and this model, would be rare in the sense that the solar system with the conditions for life, etc., in the Earth, right?
Yes, I totally agree with you. It seems that the solar system is very special, and we need to might need this reduction of the pebble flux to make maybe something like the Earth. And then we have also to have, as I said in the very end of the talk, it was a little bit, I have to speed up a little bit, and then maybe it was not super clear, but to have this giant planet instability that was maybe also another atypical event compared to most of the giant planets and other systems that have very eccentric orbits. And then you have also maybe somehow avoided the migration of Jupiter even during the early stages to become a hot Jupiter maybe. And it's or maybe even a planet, not hot Jupiter essentially, but a planet that could have migrated all the way from 5 up to 1 AU. and perhaps prevent the formation of the Earth where it is, and who knows. And yeah, it's I agree with you. It's very intriguing. The solar system is very intriguing.
Thanks.
So I have another question. Because you showed the two scenarios for the planet formation, when the planetesimals, I think they start below the snow line, and after this, and above the snow line. And in both scenarios, at least some amount of planets with ice and water are formed. Does it mean that in planetary systems, there is always a high chance to have some planets with ice and water? Or we cannot draw conclusions from?
We don't know yet. We don't know. It's quite intriguing that most of the super Earths that we observe, at least the innermost ones, seems to be rocky, because as I said, in this Pebble accretion scenario, it's much easier to produce planets beyond the snow line, and once they grow, they migrate towards. But maybe the ingredients, as I said, this all depends on the here. Yeah, this. So this. Can you see it?
Not yet.
Okay. So here, so in this. Yeah, for example, the outcome of these models depends essentially where you put your seeds or your first planetary embryos in the dust, and we don't know exactly where planetesimal formation starts. So that's one big question that we have to understand. If planetesimal formation happens first at the snow line, because the snow line has, for example, the best conditions to trigger what we call streaming instability, or the collapse of these pebble clumps. Or if it maybe that's not the correct answer, maybe somehow planetesimal formation starts in the inner disk, or even everywhere in the disk. We don't know exactly where planetesimal formation starts. That's why we test these different models, and they give different outcomes. But we don't know from theoretical point of view, and we also don't have a lot of information about planets, or in terms of composition, what the composition of planets at larger distance from the stars. So it's very complicated to speculate about this right now, I think.
Right. Professor Silvio has here, he put a question in YouTube. Mm-hmm. How long this interpretation on the formation of Earth planets is affected by the bias and the discovery techniques used to know?
If you can, for example, characterize this rocky super Earths or super Earths a little bit better in terms of composition the next, I don't know, maybe 10 years, then you might be able to constrain the models. But we have been doing a lot of improvement also from the theoretical side, and I think we might have some better answers, for example, in terms of when and where planetesimal accretion starts, from perhaps first from theoretical side, then from observational point of view. And yeah, that's a complicated question, Silvio.
Right. I think Betty has do you have another question, Betty? Or maybe you just left the hand raised. Betty? Okay, I think maybe it's just the button of raise hands that she forgot it left. Okay, so would you like to thank you a lot again for the talk, André. I hope next time it will be in IAG. I believe you already gave talks in IAG, right?
Yeah.
It's the first time.
Yeah. Yeah, it's always good to have the opportunities. IAG is great. Yeah, hopefully soon you'll be able to meet in person, and yeah.
There's also someone from public is acknowledging this. Would like to say thank you, Gabriel, and everyone. So thanks a lot, André. If you have some minutes, we can talk a little bit informally. And I would like first to also to thank everyone following in Google Meet, in YouTube. And now we will finish the transmission and see you next week. So Richard, yeah. Thank you.